something.
Yeah,
And then it was like, I feel like I did all this wrong.
Yeah, I did it in the first like half an hour, and then I'm like, I should look back, and I looked back and changed like all of the answers.
So what do you want to talk about?
Can we do integration by parts?
Definite integration by parts.
Yeah. If that's even a thing, because that was the problem. Is that I didn't remember doing.
I think it's a thing, but just like the form, like how you have to.
That's the thing is that I know how to do it, but since it was a definite one, like it had boundaries, I was like, I'm not even sure how to go about it.
Maybe something like that. Right, so,
Sure, that looks about right.
So something like that where, it's the product of two functions that you know how to do calculus on each of them. But since it's the product, it's like, well, then the integral's a little bit harder and you have to use integration by parts, right? So just to remind everybody, integration by parts is this, right? So it's the integral of the product of two functions, which we usually call u, and then the other one's called dv. But the product of two functions, you can take the integral of that by replacing it with u times v, and then minus the integral of v du. Right, so I'm sure you've seen this a million times by now. Key thing to understand is that you're swapping one integral out for a new integral, and as you do so, you're swapping one piece for its derivative, right? You're swapping u with its derivative du, and you're swapping dv with its antiderivative v. So the point is you're choosing one of these to be u and the other one to be dv, and in doing so, you're choosing which one you're going to replace with its derivative and which one you're going to replace with its antiderivative, right? So more or less, I mean, technically there's lots of options, but more or less there's really two options here. We could either say, let this be u and let this be v. So we'll be taking the derivative of this and the antiderivative of that. Or we could go the other way. We could let this be v and this be u. And then we'll be taking the derivative of this and the antiderivative of that. So to figure out which one is the move, let's just look at some derivatives, right? If we go for derivatives on this one, it's going to be looking more like this. Right, so that's what happens as we take derivatives on that guy. If we choose to take antiderivatives on this guy, it looks like this. Oops, that's the 5. Right, so you know how polynomials work and how power rule works, right? So that's what's up with this guy. If we choose to do, if we let him be u, then we're going to go this way. But if we let him be v, then we're going to be going this way, right? So that's those are our options there. How about natural log? If we go for derivatives on the natural log, first thing will be 1 over x, and then after that it's just power rule. Right, so that's x to the negative 1, so this is negative x to the negative 2. And then this is going to be positive 2 x to the negative 3, and so on. So you're just going to get further, you're just going to get more negative powers of x after that. That's if we chose natural log to be u, and so we're taking derivatives of that. What would it be like if we went the other way? What if we let natural log be dv, and we had to take its antiderivative? Does anybody know the antiderivative of natural log? Yeah, yeah. Whether you know or not, it's actually kind of complicated, so it's actually kind of not the move to go this way. I believe, if I'm not mistaken, it's this, or wait, no, maybe it's...
Well, that's its absolute value.
Maybe it's this. What's that?
No, I'm just thinking out loud, sorry.
There is some weird stuff with the absolute value in the natural
Okay,
log.
I thought so.
Low key, and not to worry about it.
Okay.
But, yeah. So the point is, if you go this way, it gets worse. Is the point, right? So this guy pretty much gets, kind of gets worse this way, but not in a very handleable way, and it kind of gets better this way, but not really that much. Whereas this guy totally gets worse this way, and then changes into a totally different but more manageable form this way. So in my opinion, looking at these options, it seems like it's the move to make this be u, and so then we'll be taking the derivative like this, and therefore then we'll let this be dv, and so we'll be taking the antiderivative like that, right? So yeah, so let's go. Here we go. So how do you handle the bounds? How do you handle the bounds? There's like a way to handle the bounds, you can say like, a to b is like, you do this part and then you plug in here, and then you also do this. In my opinion, the simplest way to handle integration by parts definite is simply to do the indefinite integral all the way till the end, and then once you've got the general antiderivative, then you just worry about the bounds at the very end like that, so you don't have to do. Yeah. So what I mean is, for 1 to 14, let's just instead consider the indefinite integral of that same function, and then go through the motions here. So, as I said, I think it would be wise to let this be u, and then let the rest of it be the dv. And so according to the formula, this is going to work out to be u times v. So u times v. Right, so I wrote it over here, but let me write it again. If u is the natural log of x, then du is 1 over x dx. And if dv is x cubed dx, well then v is 1/4 x cubed. Right, so there's the u and dv that I chose in the original, and then therefore there's also the du and the v that I can fill in the rest of the formula with. So u times v is ln of x times 1/4 x to the 4 minus integral of v du. So minus 1/4 x to the 4 du, which is 1 over x dx. Right, so that was u times v. So yeah. So does everybody see what I've done here? All right, I'm following that formula to replace one integral, which I had already and was hard to figure out, and I don't know how to do it. Replaced it with a new integral, which is different than the one I had before, and hopefully is one that I actually can figure out. And in this case, yes, I can, right? Because in this case, this, instead of this polynomial part and this logarithm part being like uncombinable and being like two different things that I couldn't simplify, well now they're the same type of thing, and so they do combine together. And so it becomes natural log of x times 1 over 4 x to the 4 minus, so this and this can cancel a little bit, and it's 1/4 x cubed. And that means when I take the integral, first of all, I'll take this 1/4 and put it over here. When I take the integral, this is just power rule, and so we just gain another factor of 4, like that. Right. So let me get rid of all this. So the point is, we just used integration by parts to solve this integral, right? To solve this integral of x cubed natural log of x dx. It turns out the antiderivative of that is x to the 4 natural log of x times the fourth minus 1/16 x to the 4 plus z. So yeah. So then finally, what we were really looking for, I'll get rid of this now. What we were really looking for was the definite integral. And so here's my strategy for handling definite integrals with integration by parts, is you just pretend it was not a definite integral and you just do it this way. And you just do it all the way through, you don't worry about the bounds until the very end, and now that you're like, okay, so now I have to plug in the bounds. Boom. And so you just do that at the end. Now you may know that when you plug in the bounds, the c, whatever that c is going to cancel out, so you might as well just not even write the plus c if you want. But then you just plug in the bounds at the very end. So you don't have to do any special stuff with the bounds, you just do it regular the whole way through, you get the antiderivative the whole way through, and then you're done, and then you can kind of clean up the situation and not worry about how you just did that. And there you go. So there's your function, there's your antiderivative, then you plug in the bounds top and bottom like that. So yeah. So there is a version that plugs in the bounds halfway through. I find that confusing and not useful, because you can just do it the whole way through. So yeah. Okay, so that was a sort of random example of integration by parts. Anybody else got anything they want to go over? Or anything like that? How can I be most helpful to you in this time? You got anything you're trying to talk about?
There was this one problem on the test. It was the integral. It was a definite integral, but it was the integral of x to the third times cosine x. No, x to the fifth times cosine x to the third.
Oh, I know what you're talking about.
Yeah, I think that was the first one.
Yeah, that was the first one.
Okay, let's see.
That's the one I tried to do integration by parts on.
I don't think it's possible. I gotta get the first part up to where you find the u. After that, I just.
First one was coming zero.
Huh?
First one was coming zero.
And I think it was over -1 and 1, something like that.
Oh, well, wait a second.
Yeah.
It should be zero. It should be zero straight up.
Huh?
The answer should be zero.
The answer should be 0. Yeah, why do you think that?
Because cos is it's an odd function.
That's what I put on the test because that was the last thing I could think of. But
Yeah, so for anybody who didn't hear that, this is a cool thing you can be aware of, right? Notice that the interval that we're integrating over is actually symmetric about the origin, right? It's the same on both sides. And I don't know what this graph looks like exactly, but I'll tell you one thing I do know. Cosine is an even function, and what that means is it looks the same left and right. Or in other words, the area from, let's say, 0 to 3 is going to be the same as the area from -3 to 0. Right? That's what it means to be an even function. I'm used to drawing on a computer, and I keep thinking I have a simple undo button, but I do not. So check it out, though. So this is an even. This you don't need to know about this, but this is a useful thing to know. Is that an even function times an odd function is an odd function. And it's best when you're trying to think through that stuff, best to think about monomials as an example. An even function times an odd function like this, right, even odd, is an odd function. And so even for non-monomials, it still works like that. An even function times an odd function is an odd function. And what that means, odd functions, what the heck have I done here? This is the wrong. Odd functions be like this. So sine is an example. I should have drawn a different example. How about something that goes like some stuff, I don't know, something like that. The point is, the way that the odd functions work is the area to the right of the graph and the area to the left of the graph are always the same. Now let me see if I can. It would be really cool. It would be cool if this would work. Honestly, though, I don't think that's going to happen. No, yeah, this is it. I'd say PC. Okay, all right, look, here we go. Displus.com/calculator. This is the best calculator website. This is the best graphing calculator website. Let me just say that Texas Instruments is low-key scamming our country. So anyway, so let me just show you real quick. Here's an example of an odd function, right? Or also something like this, right? X to an odd power. These are both odd functions. And notice the thing about them is that the area under them to the right side and the left side are exactly matched, but they're negatives of each other, right? Because one side goes up and one side goes down. And that's how it is with all functions that are called odd functions. And even functions, on the other hand, like this one, or like this one, they're symmetric. The areas are matched on both sides. They're either both positive or they're both negative on both sides. So the point is, if I'm looking at this thing and I can see, holy moly, look at that, what an absolute monstrosity. Because it's getting so much faster. It's getting faster by x cubed, so it's going nuts over there. But anyway, just looking in here, this is an odd function. You can see that what's going on the right-hand side and on the left-hand side are the same. So this seemingly difficult-looking integral, the integral from -1 to 1 of x to the 5 cosine of x cubed, is indeed 0. Is indeed 0, no calculations required. I don't need to sit here and figure out an antiderivative of that. I know that the two sides are going to match up because this area, the area between yeah, right. This area over here is exactly matched with the same area over there, so they're guaranteed to cancel out. So you don't need to do it. So yeah, so that's one way to do it. Is if you know that that's a what do you call it? An odd function that's like that, then you can do it that way. But you also can do it without doing that. There's also a way to do this one the other way. Did anybody actually do this integral straight up? Oh no.
Not correctly.
I think I ended up with, I didn't do it right because then at one part, wouldn't you have to do integral by parts since I'm multiplying?
Yeah.
So that's where I messed up because I
The one fell over.
didn't know. Oh yeah, it's in front of the desk.
Oh, thanks.
You're welcome.
I just gave up and just wrote what.
I think I did end up putting 0 because I was like, you know what? I'm just gonna plug them in, and I think when you end up putting everything in, it ends up canceling anyways.
Yeah.
Because I think I redid this problem because I knew I did it wrong and I had extra time, but I ended up with 0 twice. So I was like, well, I guess it's 0.
Raise your hand if you want to go through this one the long way.
You're gonna make me suffer.
Yeah, I love it. I'm happy to do it. So.
See,
Just in case there's these types of questions.
You're right. Okay.
But are there any? And again, this is for you guys. So if literally anybody in this class has something that they want to go over, tell me what it is, and I will happily do it. I will happily do it. Okay. All right. Here we go. So first thing I see with this, that's no good. Hate that. Hate to have a complicated thing on the inside of an already, its own function. So whenever possible, it's great to give this. One of these, a good old U substitution, and hopefully, so this will just be U, and then hopefully I can work out the rest of it. But we'll see if it works out or not. Right. So there's my.
right.
There's my.
That's it. Yay!
Oh, see, well, wait a second.
But then I also tried I know in the homework it said if you make one where you can find the derivative that includes the outside, it could also help.
Yeah.
So I put x to the 6th,
Okay.
but then I got lost.
Oh, I see.
But then I got lost about how to plug that into du.
Yeah. Okay, so check it out. So so use substitution, right? So we're making a change of variables here.
I'm just gonna plug stuff in.
And the reason we're making this change is so that we can do this. Right? So instead of this cosine of x cubed, that's no good. We want it to just be cosine of one single variable if we can. So that's a good switch to make. But the challenge is now we have to write the entire integral in terms of that new variable. So this dx and that x to the 5 are no good.
Instead take it root
What's that?
root of u. Cos root
No, because I went with x cubed, not x to the 6. If I had gone with x cubed, if I had gone with x to the 6, then it would be cube root x. Or square square root of u, yeah. So I'm showing it this way first, and then I'll try doing it the way that you suggested. So we gotta manipulate this until it's all used, right? So the dx, we've got this situation, right? We've got du equals 3x squared dx. So what I want to do actually is I have a dx here, and I have many x's here. So one thing that I'd probably want to do is take two of them, right? So split this up, right? X to the 5 is really x, right? So 3 of them I'm going to leave out front, but then 2 of them I'm going to put over here. And the reason I'm doing that is because I'm trying to get this. I'm trying to get this 3x squared dx. And so now the way I've written it is I've got my x squared dx. All I need is the 3. Well, the trick to getting that 3 is you can always add a
1/3.
3 as long as you also add a 1/3, right? So that's a totally valid thing to do as long as I account for it over there. And the reason I want to do that is because now that's my du, right? So the thing I'm trying to accomplish is turn everything into u's, and the hard part of that is usually turning the dx into the du. But I've just done it, right? I know that I need a 3x squared, and so there we go. I just got my 3x squared. So this is now my du. And then what's this? Well, fortunately, that's exactly u again. So this is actually, all right, this is getting ridiculous. I need to stay organized. These are all not mine. The literally the big black one. Anybody seen this big black marker?
I
I
don't
didn't
think
hear it
anything
drop.
fell. Yeah, I didn't hear anything fall off.
Unbelievable.
Check your pockets.
They're not there. Okay. Oh, aha. Okay. All right. So, what the hell was I talking about? Oh yeah. So this is so we have succeeded in making the switch. All x's have now been replaced with u's. This here is u, and then cosine of u du. There we go. So using this u substitution, using this change of variables, we took a really complicated looking integral involving a variable to the 5th power to another integral which is, of a similar form but definitely less complicated. And it turns out that these two integrals are equivalent. So yeah. So now all we got to do is figure out this integral, and then we should be good to go. Now maybe I shouldn't have used the letter u, because now we got to use the integration by parts formula, which calls something the letter u. So that's kind of confusing. But we'll just have to handle that. So the integral of u dv is u times v minus the integral of v du. And so yeah, so as usual, right? You got to pick one of these two things that you want. One of the things here you're going to be taking the derivative, and the other one you're going to be taking the integral. This one I could either derivative it to get 1, or I could integrate it to get 1/2 u squared. This one I could either derivative to get negative sign or integrate to get positive sign. So this one, I'm sure you'll agree, it doesn't really matter whether we go up or down, as we're getting sine either way. But this one, I'm sure you'll agree, it's better to take the derivative and turn this into 1 instead of take the antiderivative and turn this into u squared. So yeah, so letting this be appropriately u, and then the other stuff be the dv, is totally the move. Totally the move. Right, that would be u, and this would be our dv. Right? So if, geez, yeah. So the double variables thing might be a little confusing, but that u and that u we're calling the same, and then same thing for the derivatives. But then dv was the rest of it, which means v is sine. Okay, so then we just follow that formula. Right, don't forget the 1/3. So 1/3 times uv minus the integral of v du. Okay? And then finally now, we're at an integral that we can actually do. Right? So we don't have to do integration by parts anymore. We finally come to the end, right? We turned an integral which we couldn't do into a simpler integral which we still couldn't do. But then we used integration by parts to turn that into another integral which we can do. Right? And then we're done. Right? So this is 1/3 u sine of u. So let's see. So the integral of that would be negative cosine. But since it's already negative, it's positive cosine. And then plus c. So then finally, u is actually a variable that we made up. We'll put that back. It was actually x cubed. So altogether, this is 1/3 x cubed sine of x cubed plus, I'm distributing this 1/3 here, 1/3 cosine of x cubed, and then plus c. Right, so plus c, but then they said, go from -1 to 1, and so here you can find out for yourself that yeah, if you plug in -1 to 1, right? If you plug in, not plus c, plug in -1 to 1, right, you're going to get 1/3 -1 cubed sine of -1 cubed plus 1/3 cosine of -1 cubed minus 1/3 1 cubed sine of 1 cubed plus 1/3, well, minus that entire thing, cosine of 1 cubed, right? And everybody cancels out is the point, right? So this is a little long-winded. Everything cancels out is the point. Because these are the same, and then these are, well, no, these are negatives of each other, and these are also negatives of each other, so then these are the same, and so then they disappear, and then these are exactly the same, so then they disappear. So yeah. Okay. Right. What are y'all thinking? Anyone got anything else? Any question or concept or anything from the exam or perhaps from whatever's coming next?
I don't think so. I can't think of anything.
You two in the back? Nothing? Oh, well, you're not really in the back, the middle.
I was like, who's behind me?
Okay. All right. Well, I guess that's it then. I guess I got nothing else to say. So yeah, I don't know. All right. Hope you all did well on the exam. Haven't checked them out yet.
Oh. Are you grading them?
Yeah, I am.
All right, I'm gonna see myself out.
Have mercy on us.
I'll try.
You take bribes?
I'm afraid I don't do anything like that.
Alright.
Wait, what's up?
You will be grading the test.
Me? I will be grading the test. Yeah. Yeah, I'll be grading the test. Probably right now, actually.
Give it back to us.
Do you wanna grade mine right now in person?
No.